Alright, welcome back guys. We're going to look at this review for the Module 4 exam, or Chapter 9 exam. And it consists of 20 questions, okay? Alright, and they go in order, okay? So, number 1, it says, let's let f of x be this linear function, and g of x is this quadratic. And we want to find f composed of g of negative 4. Well, what we're doing here, guys, is really just plugging negative 4 into g, and then whatever value we get from that, we plug that in to f, okay? So if I plug negative 4 into g, and you gotta be careful with these negatives. You need to keep it in parentheses, because when you square a negative, you get a positive. So I'll have negative 4 squared, which is 16, plus 2 is 18, and that's what's going to go in my function f. Okay, so now I need to find f of 18. So I would have negative 2 times 18, and then minus 1, and I believe that's going to give me negative 37. On that one. Alright, number 2. Number 2 says we want to find these two compositions, but we're not plugging in numbers. We want to find f composed of g, and then g composed of f. Okay. So in both cases, guys, we're just plugging one function in to the other function. So with this first one here, I'm going to be plugging g into f. So in other words, all of this for g into the x that's in f. And if I do that, I'll get x minus 23 plus 23. And guys, when you take away the parentheses, the 23s are going to cancel. You're just going to be left with x. And then really the same thing's going to happen when you go in reverse, when you plug f into g. Technically, you would end up with x plus 23 minus 23, and the same thing's going to happen. You're just going to get x. Okay. Now, as far as the domain of these new functions is concerned, because both of these functions were linear polynomials, any sort of composition is going to be another polynomial, and consequently the domain is going to be all real numbers. So in interval notation for both of these, it's just going to be negative infinity to positive infinity. Alright, number 3, it says use the horizontal line test to determine whether the function is 1 to 1. Well, guys, this is a parabola, an upside down parabola. This would not pass the horizontal line test. Okay, so it is not a 1 to 1 function. Now you remember, in order for us to find the inverse of a function, the function itself has to be 1 to 1. And so with these quadratic functions like this one, what we did was we restricted the domain. Alright, but in any case, number 4 says determine whether this guy's 1 to 1, and if it is, find its inverse. Well, all of these are going to be 1 to 1. Okay, x minus 9 is just a linear function, so it would pass the horizontal line test. And to actually find its inverse, you remember that 4-step process. You replace the f of x with y, and then you swap the x and the y, and then you solve it for y. So with one like this, to solve for y, all we're going to have to do is add 9 to both sides, and we get y is equal to x plus 9. And then if I want to, I can use that inverse notation. I could say f inverse of x is equal to y plus 9. Or not y, but x plus 9. Okay. That's actually what these two functions up here were, guys. These were inverses of each other. That's why every time you composed one with another, you always got x. Number 5 is the same type of question. This is a square root function. It's an increasing function, strictly increasing. So it is 1 to 1. Now to find its inverse, you do it the same way. It's just that there's a little bit more work. So I'm going to swap my x and y's. And then I need to solve this for y, okay? So I need to get rid of this square root, and the way we do that is by squaring both sides. So when we square a square root, we end up with just what's underneath it. And then, of course, on the left-hand side, we end up getting x squared. And then as far as solving this for y, all I need to do is subtract 4 from both sides. And I'll get y is equal to x squared minus 4. Okay. Now, technically, you should restrict the domain. But you don't actually have to know that to figure out which choice it's going to be. The domain has to be restricted only to values of x that are greater than or equal to 0. Okay? Because that's what the range of this original function is. That original square root function stays strictly above the x-axis. And so the domain for my inverse function needs to be strictly above the x-axis. Okay? Or, excuse me, strictly to the right of the y-axis. Anyway, it's going to be choice B. Okay. All right. Number 6. So it says graph the equation on paper and then choose the correct graph. Well, guys, this is an exponential function. It's 2 to the power of x. So you know it can't be choice A or choice B or choice C. It's got to be choice D. But if you're not sure, you can always graph it in your calculator. Okay. Choice C is actually the graph of a logarithmic function. Choice A is the graph of a linear function, and choice B is the graph of a quadratic function. All right, number 7 here. So what we've got going on here, guys, is this is a transformation of some basic function. And that basic function would just be 2 to the x. So we're going to start with the graph of y equals 2 to the x, and then we're going to shift it to the left. Because this says x plus 4, it actually shifts horizontally to the left 4 units. And then we would shift it down 2, because this minus 2 right here will shift all those ordered pairs down 2. Okay? And then your last step is just going to be to graph it. So remember, when you're graphing these in the software, you need to make sure your base is 2. Sometimes you have to change it. And then you just dial in these transformations by moving those sliders. All right, number 8 here. So this is this situation here exhibits exponential growth. Okay, remember us talking about the growth of an investment that earns compound interest. So it says on Melissa's 6th birthday, she gets a $6,000 CD that earns 5% interest compounded quarterly. If the CD matures on her 11th birthday, how much money will be available? So guys, this is the way we expressed it in class. We call it A for accumulated value. It's a function of t, or time, and it's the principal times 1 plus the APR, or the interest rate, divided by the number of compounding periods in a year, and you raise this to the exponent of the number of compounding periods times, the number of years, which is time, okay? So it's an exponential function because our variable here is t, and it's in the exponent's place. So all you're going to do is you're going to plug the values into these parameters and evaluate it. So P is $6,000, the APR is 0.05, because that's what 5% would be as a decimal. And if it's compounded quarterly, that means it's done 4 times a year. So your value of N would be 4. And then if it's from her 6th to 11th birthday, that's a time span of 5 years. And so I'm going to model this in the calculator. Guys, you can type it in exactly the way you would write it. 6,000 times, in parentheses, 1 plus 0.05 divided by 4, because it's quarterly compounding. We're going to raise this to the power of N, which is 4 times 5 for T, because we're talking about 5 years. And we hit enter. This is the amount. It says round to the nearest cent, so this would be $7,692.22. Okay, so just make sure you guys round to the nearest cent. All right, now we're getting into, this would be 9.4 on logarithms. It says find the logarithm. So this is the common log base 10 of 1,000th. Guys, these can be done in your calculator if you want, or you can work them out by hand. 1,000th is the same as 1 over 1,000. So you could work these out like we did in 9.4 by hand if you want, but I would just type them in your calculator. Okay, it's going to be, should be -3. And then this one here, what you could do here is realize that you got log base 4. You remember, you can convert any radical into an exponential expression. This little 4 has a little understood exponent of 1, so this is really the same as 4 to the power of 1/7, okay? It's the exponent over the index. So the 7th root of 4 is the same as 4 to the 1/7. And if you remember, a logarithm is just an exponent. Well, the exponent is right here. Okay, so the value of this is 1/7. Now you could also do this in your calculator, but you have to come over here to math, come over here to number. No, I don't think it's in this one. It's under math. And then scroll down. There it is. Choice A. Hit enter, and it will allow you to put in your own base. But then for the 7th root of 4, what you have to do is come over here to math again and come down here to number 5, where it's got an X right there for the index, because this is not a square root or a cube root. And then you can give it an index of 7, and then put a 4 in there. Now when you hit enter, it's going to give you a decimal, so you would have to convert this back to a fraction, okay, to get 1/7. All right, number 11, convert, let me zoom in a little bit, convert to a logarithmic equation. Okay, so what we do here is we leave the u in place. We just add a log to it. This becomes log base u, and then we swap the k and the 125. So 125 becomes the argument of the logarithm, and the k goes to the other side. So now this is a logarithmic equation. And very similar here where it says convert to an exponential equation. The base of this logarithm is an understood 10. So going from a logarithmic equation to an exponential equation, you're going to throw away the log, keep the base, and then swap the -4 and the 0.0001. Okay, and that's it. That's your equivalent exponential equation. All right. And then number 13, it says use a calculator to find the common logarithm. Well, if it's a common logarithm, then we could just type in there log of 87, and we're going to get a decimal approximation because technically that's an irrational number. And it says round to 4 decimal places. So to 4 decimal places, this would be 1.9395. Okay. All right, and number 14, now we're getting into 9.5, where we're working with those properties of logarithms. So it says express as a product. So here you would be employing the power rule, which basically just says that you can take that power 11 and move it out in front, and this becomes 11 times the common log of just s. And the 10 you don't actually have to even write. Okay. Number 15, rewrite as sums or differences of logarithms. So here what we're going to be doing is expanding this. So we're going to start off using the product rule because this is log base b of this product. So that just means you split this into 3 logarithms, and they're all separated with addition, okay? 1 for each of those factors. Y to the 4th, and then log base b of just z. Now you've got one last step here. You can use the power rule and actually move those powers out in front of these logarithms. And so if you do that, you get 3 times log base b of x plus 4 times log base b of y plus, and then this last one's just going to stay the same, log base b of z. Okay. All right, number 16. It says express as a single logarithm and if possible simplify. So here what we're doing is condensing. We're starting out with 2 logarithms. We're going to condense it down into 1. Now these 2 common logs are separated with subtraction. And so we're going to utilize the quotient rule to condense them down into just 1. So it'll be the common log of the numerator will be that first argument, which is 1,000,000, divided by, and the denominator will be that second argument, which is 100. And guys, to simplify this, you can divide 1,000,000 by 100, and you're going to get 10,000, I believe, because you just knock off 2 zeros right here. So you'll end up with a common log, well, I could write this over here, common log of 10,000, and that can actually be evaluated. You could do it in your calculator, or you could think 10 to what power would be 10,000, and that power would be 4. Actually, guys, you could have put this whole thing in your calculator, and it would have given you 4. All right, number 17. Well, this will take us to 9.6, where we're solving those exponential and logarithmic equations. Okay, solve for x. So guys, this is one in which I can equate the bases, because I know that 256 can be rewritten as a power of 4. And we've got a base of 4 over here. So if you're not sure, just try a few powers of 4. 4 to the 4th is 256. So what I could do is I could say 4 to the 4x minus 7 is equal to, and instead of 256, you put 4 to the 4th. So now that we've equated these bases, for this to be an equation implies that these two exponents have to be equal, and so you then equate exponents, and that's how you solve this, okay? Solve it for x. So I would add 7 to both sides. I'd be left with 4x is equal to 11, and I divide both sides by 4, and I get x is equal to 11/4. All right, and then number 18. So number 18 is one in which we cannot equate the bases. Okay, so what we have to do is take the logarithm of both sides of the equation. And I'm going to use the natural logarithm again. So the natural logarithm of e to the negative 0.66t is equal to the natural logarithm of 0.97. And so the power rule guarantees that that exponent will come out in front. Okay, we'll be left with the natural log of e. And guys, the natural log of e is just 1. Because it's like saying e to what power is equal to e? Well, e to the first. And so really here you're just left with, let me rewrite this up here, negative 0.66t is equal to the natural log of 0.97. And so to isolate for t, you'll divide both sides by that coefficient. Those will cancel. And so t is this number right here. Now if you look, it says type an integer or a decimal. So we're going to have to put this in the calculator. And we're going to round it to 4 decimal places. All right, so let's try this. It'll be the natural log of 0.97. And divide that by negative 0.66. And so to 4 decimal places, this would be 0.0462. Okay. All right, guys. I've got a couple left here. Number 19. So this one is a logarithmic equation. So with these logarithmic equations, we exponentiate them. Okay, so this is the common log of x is equal to negative 6. So if I exponentiate this, the base stays the same. The negative 6 comes over to become the exponent, and the x moves to the other side. So now I have it solved, basically. But 10 to the negative 6 is the same as, I wouldn't even worry about a decimal. because over here it says type the exact answer in simplified form. This is the same as 1 over 10 to the positive 6, which is the same as 1 over a million. Okay, so in other words, 1 millionth. All right, now let's do one more. Okay, save the best for last. All right, well, this one's not going to be as easy as the last one, because what we've got going on is we've got two logarithms, and they're on opposite sides of the equation. So what I need to do is to move one to the other side. So this negative log base 7 that I have, I'm going to move it over to the left hand side. And I'm going to do that by adding it. So if I add it to both sides, I would end up with log base 7 of x plus log base 7 of x plus 6 is equal to 1. Okay. Now what we can do is we can condense these two logarithms on the left-hand side into just one using the product rule, because they're separated with addition here. So this would become 1 log base 7 of x times x plus 6 is equal to 1. And now that we have just one logarithm, we can exponentiate this. Leave that 7 where it is, give it an exponent of 1, and then move that argument to the other side. Okay, we had 1 in the notes, just like this one. Then what we need to do is distribute this x. And this will give us x squared plus 6x is equal to 7. And this is a quadratic equation, guys. So I'm going to subtract 7 from both sides to get a 0 on the left. I'll be left with x squared plus 6x minus 7. Now I can solve this either by factoring or using the quadratic formula. I'm going to factor it. Factors of negative 7, that when combined would give me a positive 6, or a positive 7 and a negative 1. And so if I set each of these factors equal to 0, the way we've solved so many of these, I will get that x is equal to both negative 7 and positive 1. Now, you've got to look at these two solutions. The 1 will be okay, because if I plug 1 back in here for these x's, these arguments will stay positive. But if I take the negative 7 and plug back in, both of these arguments will become negative. And we know that for any logarithmic function, well, unless it's been shifted horizontally, there are no negatives in its domain. Okay, so for that reason, I'm going to have to throw away the negative 7. Which means the only solution to this one is 1. Okay. Alright guys, I guess that's it for the Chapter 9 or Module 4 test review. So it should look just like this. Okay.